mind telling me what you're doing with all these charging system parts and these test instruments, Jim?
Not at all, Tech. I'm setting up my own one-man retraining program.
Well, I thought you considered yourself a torque flight hotshot. Since when do you get to be an alternator expert?
Oh, I'm not the teacher. I'm just the learner. My boss, Bill, is going to tell me all about alternators and regulators as soon as I get these props set up.
Hi, Tech. Has Jim told you what we're up to?
That he has, Bill. Mind if I stick around and lend a word of wisdom now and then?
Not at all, Tech. If you hadn't volunteered, I would have drafted you.
It looks like Jim's collected everything we'll need, so start teaching, Bill.
To begin with, let's take a minute or two to look at the basic working parts of an alternator. Now, this is the rotor. It provides the magnetic field needed to generate voltage. The magnetic field is created by current flow through the rotor windings. Slip rings and brushes are used to connect the rotor windings to an external source of electricity. One brush is insulated and connected to the car's battery. The other is grounded to complete the rotor winding circuit. The basic field circuit includes the rotor windings, the brushes, the voltage regulator, the battery, and the connecting wires. And we'll tell you more about this circuit as soon as we cover the other basic parts of the alternator. This is the stator. It contains the windings or conductors that are cut by the rotating rotor field.
Are there any electrical connections between the stator and the rotor?
No, my boy. The stator windings are connected through rectifiers to the alternator output terminal, which in turn is connected to the battery. The only connection between the rotor and the stator is through their common ground. This common ground completes the circuit to the negative battery post. Does that answer your question?
Yep, but I've got another. Where and how do these rectifiers get into the act?
Those rectifiers are connected into the main charging circuit. But let me tell you why we need them and give you a simplified explanation of how they work. The rotating rotor field generates an alternating voltage and causes an alternating current flow through the stator windings.
And you can't use an alternating current to charge a battery, right?
Correct, Jim. And that's why we need rectifiers. And basically, a rectifier is a one-way electrical flow valve. It lets current flow in one direction, prevents current flow in the other direction.
What's the difference between positive and negative rectifiers?
A positive rectifier allows current to flow from the lead wire to the rectifier base. A negative rectifier permits flow from the base to the lead wire. In our alternator, 3 positive rectifiers are pressed into a holder called a heat sink. The heat sink is electrically insulated from the alternator end frame. Its function is to carry heat away from the rectifiers so that they won't be damaged by high temperatures. The positive rectifiers are connected electrically between the stator windings and the output terminal of the alternator. In other words, the rectifiers are connected so that current flow is always from stator windings to output terminal. The 3 negative rectifiers are pressed into the end frame. Electrically, the end frame is the negative terminal of the alternator. The lead ends of the rectifiers are connected to the stator windings. The rectifiers are connected so that the direction of current flow is from the end frame to the stator. To summarize, the positive rectifiers connected to the output terminal and the negative rectifiers connected to the ground side of the stator circuit control the direction of current flow to the output terminal. As a result, direct current only is delivered to the battery and the car's electrical system.
That's what I call a simplified but mighty good functional explanation of the rectifiers.
It must have been pretty simple, Tech. For the first time, I understand how those rectifiers fit into the charging system picture. Can you do as well on the regulator?
Well, I'll give it a good try, Jim. The regulator controls alternator output voltage by regulating current flow to the rotor windings. A line voltage is applied to the ignition terminal of the regulator. Controlled current is delivered to the rotor through the insulated brush and slip ring. The regulator has fixed upper and lower contacts. Now, a movable contact is attached to a spring-loaded armature. A voltage coil completes the basic working parts on this side of the regulator. There are 3 resistors on the underside of the regulator. Now, 2 of these are used in the control circuit to reduce current flow. The primary purpose of the 3rd one is to reduce arcing across the regulator points.
The amount of current flowing through the regulator depends on the position of the movable contact relative to the fixed contacts. I think this drawing will help Bill explain how the regulator works.
It sure will, Tech. Battery, or more exactly, line voltage, is applied to the voltage coil when the ignition switch is turned on. Current flow through the voltage coil produces a magnetic field. The magnetic field of the voltage coil attracts the armature, tries to pull it downward. The amount of pull on the armature depends on the strength of the field, which, in turn, depends on the amount of line voltage pushing current through the coil. When the line voltage is relatively low, the voltage coil field is weak, not strong enough to pull the armature down and break the contact between the upper contact and the movable contact. Under this low line voltage condition, the circuit is through the upper contact to the armature. Resistance in this circuit is low, so maximum current flows to the alternator rotor windings, and this produces a strong magnetic field in the alternator for maximum alternator output. When alternator output and line voltage increases, the voltage coil field pulls the armature and the movable contact away from the fixed upper contact. Now, we usually call this the float position. In the float position, the circuit is through the 2 resistors and then to the alternator rotor. Now, since the 2 resistors reduce current flow, the rotor field strength is reduced. This in turn reduces alternator output.
When the car's electrical system is calling for relatively high alternator output, the armature vibrates between the upper contact and the float position. Any questions before Bill explains the lower contact circuit?
None so far. You're getting through to me real good.
When electrical loads are light and engine speed is high, alternator output voltage tends to increase. Increased voltage pushes more current through the voltage coil, and the strong voltage coil field pulls the armature down against the lower contact. When the movable contact is against the lower contact, there's a direct circuit through the armature and to ground through the lower fixed contact. The rotor field circuit is momentarily bypassed. The alternator field starts to collapse, and alternator output is momentarily interrupted.
This interruption doesn't last very long. As a matter of fact, the armature and movable contact vibrates between the float position and the lower contact. This action controls field current and output voltage when electrical demand is low and engine speed is high. Any questions on the regulator, Jim?
Just one, Tech. Can you explain how these 2 fusible wires fit into the regulator circuit?
Sure thing, Jim. One fusible wire completes the circuit between the upper contact and the input side of the resistors. The other one completes the circuit from the lower contact to ground.
I get it. If the upper contact fuse wire burns out, you lose the circuit that gives you high alternator field current and full alternator output. If you lose the lower contact fuse wire, you lose the ground circuit and you won't get full voltage control under light electrical load and high-speed conditions. I can see where understanding how these units work is going to help me understand charging system troubleshooting.
I also think it'll help if you have a clear-cut idea of the 2 main charging system circuits, namely the complete field or voltage control circuit and the alternator output or main charging circuit.
I sure agree with that, Tech. The field circuit and the main charging system circuit follow the same path from the battery to the ammeter. Now, this common circuit goes from battery to the starter relay, through the bulkhead connector, and through the ammeter. Here, the 2 circuits split. The field circuit goes from the ammeter, through the ignition switch, back through the bulkhead connector to one of the ballast resistor terminals. through the regulator, and through the rotor windings to ground. A high resistance anywhere in this circuit will affect voltage regulation and alternator output. So the first thing to test is field circuit resistance.
Before we can talk about testing, someone better turn the record. Before you run any of the charging system tests, make sure the battery is fully charged and in good condition. And always disconnect the battery before connecting test instruments.
Those are good points to remember, Jim. Now, field circuit resistance is measured by making a voltage drop test across the circuit from the field terminal of the regulator to the positive battery post. For voltage drop tests, use a voltmeter with a scale that reads tenths of a volt.
Be sure and disconnect one of the ignition ballast resistor leads. This opens the ignition circuit, so there won't be any current flow through the ignition circuit during this test.
Thanks, Tech. I forgot to mention that. Turn the ignition switch on and the voltmeter to the lowest scale. The voltage drop should be no more than 55 hundredths of a volt. That's 5.5 tenths.
What kind of trouble would a bigger voltage drop cause?
High field circuit resistance can cause the ammeter to fluctuate. It can also cause the regulator to over-control, resulting in a lower than normal charging rate.
So I test and correct field circuit resistance first. What comes next?
Main charging circuit resistance is next, Jim. Now this circuit goes from the battery to the starter relay, through the bulkhead connector, through the ammeter, back through the bulkhead connector, and leads to the alternator output terminal.
Here's something you should know about the ammeter in this circuit. The car ammeter does not register alternator output. It registers the amount of current flowing into or out of the battery. When the battery is fully charged, it is normal for the ammeter to register 0 because the alternator is supplying the car's electrical needs, and nothing is flowing into or out of the battery.
Tech's right. The only time there is any current flow through the entire charging system is when the alternator is sending a charging current to the battery. Current never flows from the battery to the alternator output terminal because the rectifiers won't let the current flow in that direction. Consequently, charging system voltage drop must be measured with the engine running and the alternator charging. Field regulation must be removed so that you can control current flow by adjusting engine speed. The test ammeter is connected in series between the alternator output terminal and the charging circuit wire. Also, connect a jumper from the alternator output terminal to the alternator field terminal.
Be sure and disconnect the field lead before you connect that jumper.
Connecting that jumper completes a circuit through the test ammeter and to ground through the brushes, slip rings, and rotor windings. So the ammeter will register field current flow through the alternator.
A field current of less than 2 4/10 amperes means high resistance inside the alternator, possibly bad brushes or slip rings. More than 2 8/10 amps means an internal short in the insulated brush lead or perhaps in the rotor windings. I sort of interrupted your circuit resistance test explanation, Bill, so maybe I'd better let you get back to that part of the lesson.
Okay, Tech. The voltmeter is connected across the circuit from the charging circuit wire to the positive battery post. Now, here's another place where I like to use a voltmeter with a scale that's graduated in tenths of a volt to read voltage drop. Start the engine and adjust engine speed to get a reading of 10 amperes. Your voltmeter should show a voltage drop of no more than 3/10 of a volt. If you get more than that, correct the high resistance before you go on to the next test.
Don't forget to test for resistance on the ground side of the circuit. To do this, connect your voltmeter across the ground circuit from the alternator frame to the negative battery post. With engine still running and 10 amps showing on the test ammeter, the voltage drop should be no more than 3/10 of a volt, the same as for the insulated side of the circuit. Now, If field and charging circuit resistance are within specs, you're ready to test alternator current output. This test will tell you whether or not the alternator is able to deliver specified current at a specific test speed.
Here's how we connect for that test. Leave the ammeter connected in series and the field jumper in place. The voltmeter is connected across the circuit from the alternator output terminal to the negative battery post.
That way it will register output voltage instead of voltage drop. Next, a carbon pile or battery loader is connected across the battery so you can adjust load to get the voltage specified for this test. Be sure the carbon pile is open, off position, before you connect it. You'll also need a tachometer so that you can set engine speed accurately. Now tell Jim what to do after instruments are connected and the engine is started, Bill.
Output specs are based on exact speed and voltage, so adjust engine speed to 1250 and adjust the carbon pile so that the voltmeter registers 15 volts. Your test ammeter will now show current output under controlled speed and voltage conditions.
Output specs aren't the same for all alternators, so check your reference book to make sure which alternator you're testing and which output specs apply. Now, suppose we get on with the voltage regulator tests, Bill.
Just what I had in mind, Tech. For the voltage regulator tests, leave the ammeter in series and the voltmeter across the circuit, the same as they were for the current output test. However, remove the field jumper and connect the regulator lead to the alternator field terminal to put the regulator back into the circuit. Start the engine and adjust speed to 1250. Turn on lights or accessories to put a 15 amp load on the charging system. Then, let the engine run for 15 minutes to temperature normalize the entire charging system.
Is that 15-minute warm-up really important?
It sure is, Jim. As the regulator voltage coil warms up, regulated voltage gets higher. So a setting that's okay for a cold regulator might be too high after the regulator warms up. But that's only part of it. As the regulator armature warms up, regulated voltage tends to get lower. However, the voltage coil and the armature don't warm up or normalize at the same rate. Voltage goes up and down during warm-up. So, to be on the safe side, run the engine at 1250 with a 15 amp load for 15 minutes. That way you can be sure that both the armature and the voltage coil have temperature stabilized. And speaking of temperature, voltage regulator specifications are based on a specific temperature reading taken 2 inches from the regulator cover. That's with the cover in place and after the 15-minute warm-up. After the system's normalized, but before you test the regulator, be sure and cycle the regulator. That simply means you disconnect the regulator for a split second so that the regulator voltage coil field will collapse. But I'll let Bill tell you about the voltage regulator tests.
The first test checks voltage control when the regulator is operating against the upper contact, as it does under high electrical load and relatively low engine speed. Note the voltage and temperature readings with the engine operating at 1250 and a 15 amp load on the electrical system. Check these values against the voltage temperature specifications. If voltage is higher than the maximum specification, there's probably too much armature spring tension, and it must be adjusted by bending the spring hanger. If voltage is below the minimum specification, armature spring tension is probably too low. If voltage is within specifications, you can go on to the next test. Increase engine speed to 2200 RPM. Reduce the electrical load by turning off all the lights and accessories used to get your 15 amp load for the previous test. Amperage should drop below 5 amps. Voltage should increase at least 0.2 of a volt, but it should increase no more than 0.7 of a volt above the reading taken at an engine speed of 1250. If a regulator passes this test, operation against the lower contacts is okay. If voltage increases less than 0.2 or more than 0.7, the air gap between the regulator armature and the voltage coil is probably incorrect.
I hate to ring the bell on this session, but we're rapidly running out of time. Now tell me, Jim, did this session on the charging system units and circuits help you?
It sure did, Tech.
You'll find everything we covered today in the reference book for this session. As a matter of fact, instructions for testing the alternator and regulator go into greater detail than we had time for today.
I'll be sure to keep my copy of this reference book handy.
You do that, Jim. And now, why don't all you master technicians out there review your reference books right now, while this charging system session's still fresh in your minds. Then keep those reference books and service manuals handy. And just like I said last month, don't play guessing games with a customer's car troubles. If you test, you won't have to guess. See you all next month.